Tonight on Bang Goes the Theory, Liz investigates jet lag by camping out on a sultan's private jet. I'm going to attempt to cycle to the very edge of the solar system.
Even though I've just cycled all the way from Greenwich to the edge of the Pacific, here in San Francisco, I still wouldn't have gone far enough.
And Jem gets all Evel Knievel by doing something that's never been done before. Reinventing the wheel.
Timothy, what the heck?
As far as we're aware, nobody in the world has ever jumped anything on a square-wheeled motorbike.
Do you wonder why, though? Do you wonder why?
That's Bang Goes the Theory, putting science to the test.
Welcome to Bang Goes the Theory. We start tonight with desynchronisis. That's jet lag to you and me. But what is it, and can we avoid it?
In a nutshell, jet lag is caused by our all-important body clock getting out of sync. To demonstrate that jet lag is a lot more than just feeling a bit tired, I'm going to need one of these, the former private jet of the Sultan of Oman.
Today, it's the perfect vessel to conduct a little Bang experiment. An experiment that's going to compare my body clock, the control, not getting much sleep in that thing tonight, but not going anywhere, with the body clock of a very handsome chap who's also not getting much sleep in his jet plane, but very importantly, is skipping over time zones.
The idea is that as Dallas flies back from filming in America, I'll monitor changes in his body clock.
For me, being here, the fascinating thing is the whole notion of extremophiles because, oh, sorry, I forgot to turn my phone off. Sorry, guys. Liz, I'm in America in a desert.
So what time is it over there anyway?
It's about 10:30 in the morning here, but...
And listen, have you been sampling your saliva every 2 hours?
I've been doing the swab things with the swabs and the test tubes.
Okay, and I've been doing the saliva swabs as well every 2 hours, so hopefully we'll get a good result.
All right, sorry, I'm holding the guys up. Sorry, Andy, sorry. All right, bye. Bye. Wrong number.
So, while Dallas flies home, both of us will have a bad night, but only Dallas will fly through time zones. Now, first up, we need to understand how our body clock actually works.
Our body clock's control center is called the suprachiasmatic nucleus, or the SCN. It's a small cluster of cells located in the brain that keeps all our body processes working perfectly to a daily cycle. The SCN controls everything from our sleep patterns to our body temperature. Now that's quite a big job for something that's only as small as a grain of rice.
But why do we need a body clock to work at specific times?
Well, day and night present very different challenges and opportunities for animals, so it's useful for the body to adapt itself to do certain things in the daytime, other things at nighttime. For example, we don't see well at night, so it makes sense for us to rest and regenerate at nighttime and then be active, foraging for food and digesting it in the daytime.
The SCN controls our body's functions by regulating the production of the hormone cortisol, amongst other things. And it's our levels of cortisol that will be measured over the next few hours. To shed light on how it works, I've been joined by neurobiologist Dr. Michael Hastings.
Well, cortisol is really important because it energizes us. You know, it increases heart rate, blood pressure, and it's a bit like coffee, really, if you like.
So cortisol is high in the morning.
It's high in the morning, and over the course of the day, the cortisol's gradually used up so that when we come to evening, you know, our energy levels are dipping down and we're prepared for sleep.
So when you're jet lagged and your cortisol is being released at the wrong times, it's not just your sleepiness or your wakefulness that's affected, it's actually all of your bodily functions.
It's a double whammy. First of all, our level of metabolism isn't set at the appropriate level, so we're lethargic, we can't perform as well. But making it even worse on top of that, all our different organs are operating at different clock times. So they're not working in unison as an efficient machine.
So if your liver and your stomach are doing things at the wrong time, that's why you're going to feel so rubbish.
Dysphoria.
Dysphoria?
Dysphoria, yes.
That's a cool word.
Inefficient, unable to perform, you know, to the best of your abilities.
So cortisol is incredibly important, isn't it?
Yeah, without it we'd be dead, and it really is the most important conductor of our circadian orchestra, if you like.
Well, thanks a million, Michael, but I have to kick you off my plane now because I've got to get on with my experiment. Get out.
Dr. Hastings leaves me to settle down for the night, whilst Dallas is...
I'm about to go and jump on the plane. It's noon now.
So at the start of our little experiment, he is 8,500 kilometres and 8 time zones away.
Got all my oral swab paraphernalia. Bring on the jet lag.
The idea is that whilst Dallas is whizzing through the time zones in cattle class, I'll be experiencing the same discomfort, but not actually going anywhere. Which means I've been downgraded from the Sultan's bed to servant class.
And I get to sit here now for 9 hours to mimic Dallas's flight. Ooh, that reminds me. Take another sample.
We need to sample our saliva every 2 hours by chewing on cotton swabs. They will then be analysed to show how much cortisol our bodies were producing.
But how does it produce jet lag?
Having had enough of the 1970s in-flight entertainment, I call it a night.
Right, by the time I wake up tomorrow morning, my cortisol levels will be on the rise. Dallas lands at 7:30 a.m. So his cortisol should be on the rise too. But because he's come from America, it's 11:30 p.m. for him. So his cortisol will be really low. And that's when it gets complicated because his system will be completely out of sync. And hopefully that's going to show up on our graphs. This better be worth it. Lumpy bed.
It might be 5 in the morning for me, but for Dallas, it's still 9 p.m. at night.
Everybody on the plane here thinks I'm a bit weird with my video camera, so that's why I have to sneak into the loo to do my video diary. I should really be trying to bank some sleep, but I can't because I just don't feel tired.
The next morning, although I was feeling a bit rough from my night on the seats, my body's cortisol levels were attempting to wake me up. Dallas's, on the other hand, were attempting to send him to sleep.
I'm starting to feel really tired, even though it's 7 a.m. UK time. My body thinks it's 11 p.m. West Coast American time, so my whole body is messed up and scrambled. I don't know what's going on.
With our experiment over and Dallas safely back on the ground, our samples are sent to the lab to be analysed. But what will the results show?
So when you analysed the spit samples, what did you get?
Do you want to see the details? Okay, this is a graph of 5 days, right? Daytime, nighttime, etc. These are normal cortisol levels, okay? So they're at their highest at 9 or 10 in the morning, at their lowest around about bedtime, and then they start rising again, okay?
Yep.
These are my cortisol levels.
Pretty much as normal.
Yeah, this is the night of the bad sleep on the plane, and still they're in sync with normal cortisol levels.
It wasn't that bad.
It was horrible.
It wasn't
It was
that
just
bad.
so hard, Dallas. Okay, and then the interesting bit now, your cortisol levels. So your cortisol levels when you were on the West Coast were at their highest about 8 hours after mine, which
that's
makes
normal.
sense.
That's-
Absolutely, you're in sync with West Coast time. This is the day that you landed. Now, it's 7 o'clock in the morning, but your cortisol levels are really, really low because for you, it's 11 o'clock at night.
Yeah.
It takes you about 3 days to realign to normal levels, yeah? Which isn't bad going because according to scientists, it should take up to a day per time zone you travel. So it could have taken you anything up to 8 days.
So that feels about right.
Yeah.
So is there any way of speeding up that process of getting into sync quicker?
Well, you can help it along by doing a couple of things. Like, once you get on the plane, start eating according to the times of your destination. So your organs are starting to work according to your destination time. That will help you feeling not so rotten.
I just watch movies all the time. I didn't do that.
I know, yeah,
That's
me
my
too.
problem.
I always do that. And the other thing you can do is, if you land in the daytime like Dallas, get some light because the SCN resets according to daytime hours and nighttime hours, yeah?
So talking about shifting time zones, how big do you think the entire solar system is?
Mahusive.
It is pretty big. Have a guess. Ballpark. What do you think?
100 times the distance from the Earth to the Sun, so what's that, 15 billion kilometres?
Well, they actually measure it at 10 trillion kilometres. That's a light year across.
Wow.
But what on earth does a light year mean? I wanted to try and explore that on a more human scale. And annoyingly, for some reason, NASA wouldn't lend me a space shuttle. So
I had to go to the Royal Observatory in Greenwich to start a journey that's going to take me to the very edge of the solar system. But first, a quick history lesson.
Absolutely love this. It's called an orrery, and it's a little mechanical model of our solar system. You can see the planets here orbiting the sun as they would do in real life. But it's more than just a little interesting knick-knack. It's actually the result of arguably the greatest revolution in the entire history of science.
Before the 17th century, most people believed in a geocentric universe with the Earth slap bang in the middle and everything else orbiting around it, including our sun.
It's only when the big guns, Copernicus, Galileo and Kepler, came along that our understanding shifted to a heliocentric model with the sun at the centre of things and the Earth and the other planets orbiting it. Like that.
But there's something wrong with this orrery. Its scale. All the planets are far too close together. Let me demonstrate how they should be spaced out with a scale model of my own.
Now, our sun is a fairly average-sized star. There's much bigger stars than ours in the universe. So let's represent it with this football. How far would you have to travel away from our sun football here before we reach the first planet, Mercury?
Well, on this scale, every metre is 3 million kilometres, so the answer is
18 metres, which is the equivalent of 56 million kilometres. Now, if the sun was the size of our football up there, then Mercury, by comparison, would be about the size of this grain of sand. Another 19 metres, or 52 million kilometres, you arrive at Venus.
and it's not very big, about the size of this nut.
Another 15 metres or 42 million kilometres, you come to the most incredible planet in our solar system. A place that 6.8 billion people might find strangely familiar. But how big is the Earth compared to our football sun over there? Well, not very big at all, really. About the size of this pea.
OK, next up, about 234 million kilometres from the sun, the mighty Mars.
And it's only the size of this tiny, insignificant grain of rice.
Mars represents the final frontier of the rocky inner planets. But as we move further away from the sun into the darkness of space, the planets are mainly made up of gas. First up, right at the edge of the park, it's Jupiter.
259 metres from our football-sized sun, 777 million kilometres in the real world.
It's 11 times the size of the Earth, which makes it the giant of the solar system, which on this scale is
About the size of this golf ball.
like Jupiter. The next giant of the solar system is mainly made up of gases like hydrogen and helium. You'll find it just down the street outside the park, and it's called Saturn. It's 472 metres from our football, and that's
1.5 thousand million kilometres from the sun, and about the size of this table tennis ball, but with some of them nice rings going around it.
Finally, I'm in Greenwich town proper. Next up is a lump of ice and rock, more formally known as
Uranus. It's about a kilometre from our football over there, or 2.8 thousand million kilometres from the sun. It's starting to get very cold and it's very dark.
After that, 2.2 clicks from our football is Neptune, another icy lump the size of a grape, probably a white one. OK, so travelling out from the Greenwich Observatory where we started with our football-sized sun, we've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. And until 2006, there was one more planet in our solar system, but not anymore.
Over there by the dome is poor old Pluto, everybody's favourite demoted planet, some 2 kilometres away from our football sun. That's 6,000 million kilometres away from the real sun, and smaller than the tiniest grain of sand.
But the solar system doesn't stop there. The journey from my football sun has only just begun. Way out beyond Pluto, there's the Oort cloud, made up of trillions of small, dirty snowballs locked into orbit around our sun. Now, no one is quite sure how far it extends, but estimates range from between 1 and 200,000 times further from the sun than the Earth is, which means on our scale, it may end up somewhere here, in the deserts of the western USA. But what about beyond the solar system? How far is it to the nearest star? Well, it's called Proxima Centauri, and it's so dim you can't even see it with the naked eye. At 4.2 light years away, it's a long way off, even on our football scale.
Over 14,000 kilometres, in fact, which is why, even though I've just cycled all the way from Greenwich to the edge of the Pacific here in San Francisco, I still wouldn't have gone far enough. In fact, I'd have to go about another 2,500 kilometres past Hawaii, out there somewhere. In terms of size, quite small actually compared to our football sun, because it's a red dwarf about the size of this hockey ball. That was a hell of a bike ride. Oh.
As you cycle away from the sun, does it constantly feel like you're going a little bit uphill?
Yeah, you can really feel it in your thighs. It's tough. OK, enough of that. It's time to catch up with our weekly dose of Dr. Yan and his street science. And this week, he's gone a little bit sensitive.
We all know that feeling of taking the first few steps into the sea. It's usually pretty cool, actually, even on a hot day. But soon you seem to warm up and it doesn't seem so bad after all. Well, that's thanks to our body's amazing sensitivity to changes in its surroundings and its ability to adjust and adapt. Our response to temperature is a prime example of that, but it sometimes has some rather unusual consequences. Look, I'll show you. I'd like you, when I say go, to put your hands one into that water and one into that bucket of water, OK?
Yep.
The bowls are at different temperatures. One's hot, one's cold.
Different.
Oh, hello.
So how do they feel?
Warm, hot, cold.
Cold. Different. It's different. And the reason that one's feeling cold and the other one's feeling hot is because under your skin you have millions of tiny little nerve endings called thermoreceptors. And you actually have several different sorts of thermoreceptors that respond to different temperatures, and they send a constant stream of messages to your brain. Okay?
What's happening is in cold water, our cold receptors are becoming desensitized, sending fewer cold messages to the brain. The opposite happens to the hand in hot water. It sends fewer hot messages.
So now, are we confusing my brain? Is it really confused?
Well, the interesting thing is, how do they feel now?
Warm.
Really cold.
Yeah, but are they getting a bit...
Yeah, this one is not so cold now.
Oh, it's not so cold. Yeah. So yeah, you get this thing called sensory adaptation, which means that your thermoreceptors sort of adapt to that temperature. And that means that there are fewer impulses, fewer messages being sent to the brain, and the temperature doesn't seem so extreme. Yeah? Now, what I want you to do is, when I say go, I want you to take both hands out of the water, and without drying them or anything, put them both into the blue ones. Okay? You ready? Yeah? Go. Now, how's it feel?
Opposite.
Yeah.
Oh, really?
What sort of temperature do you think the water is?
I have no idea what the temperature of the water is because my one hand is warm and the other one is cold.
Yeah, my right one's gone hot and my left one's gone cold now.
It's really weird, isn't it? I'll tell you, I've got a fancy thermometer here. If I just point it here. That one's 20 degrees, and that one is also 20.2. So, gosh, they're almost exactly the same. That's sort of room temperature. Yeah?
Doesn't feel that at all.
So basically what's happened is that the one that was in cold water, all the cold receptors have become adapted to that temperature and they're not sending messages so often. When you plunge it into the lukewarm water, all you get is the hot. And so you feel hot. And similarly, it's exactly the opposite for the other one. The one that's been in the hot water, you put it in lukewarm water, all the hot ones are sort of maxed out. They're not sending messages, you get the cold messages and that feels cold. And that's how it all works. Wow. Simple.
The amazing Dr. Yan, everybody.
Yep, never disappoints.
Never. OK, Timothy, what's up next?
In engineering, you never know how far you can push a concept until it starts going wrong. With this one, I feel that might be exactly where we're at. Wheels don't have to be round. This week, I want to try something audacious. I want to build a square-wheeled motorbike and jump it. But I'm not going to use a specialist stunt bike. I'm going to do it on the world's most popular motorbike, a Honda Cub 90. 60 million worldwide, but only this one is getting square wheels. We simply love this. You see, not even Evel Knievel attempted to jump anything on a square-wheeled motorbike. But then Evel Knievel never studied much in the way of mathematics. You see, maths is the key to making square wheels work. As the square rolls, this bump lifts the side and lets the corners drop down, keeping the axle moving in a perfectly straight line, giving me a smooth ride. That's fine whilst the wheel is idly rolling over the humps. But what happens when the wheel is powered? Will that added force shift it out of sync? Maths won't help me now. There's only one way to find out. Give it some revs. This is my worst nightmare. As soon as any power is applied to the wheel, it slips out of sync, its corners smashing into the track. With only one day to go before blast-off, I nip to the builder's yard with a last-ditch plan. That's to try and increase the grip with a coat of non-slip paint. The next day, it's make or break. Either I've solved the problem, or my unprecedented stunt will end in tears. That feels like it's going out. Yeah. But try as we might, the more power I apply, the worse it gets. Then it starts to rain. And all hopes of a jump are off for the day. As I sit here now, I can't even pretend that I feel confident. I don't mind if it goes wrong on the flat because it'll hurt, but I'll walk away from it. If it goes wrong kind of 6 or 8 feet in the air, as I get to the end of the ramp, I think that's going to be really bad, like bad in a way that I don't want to experience. And I'm properly nervous. But the thing that I'm most nervous about is it not actually working. Like, it's got to work. Because that's what I do. It's my job. It's our final day at the stunt test site. And if I'm going to jump, we've got our work cut out. The whole morning is spent repairing and reinforcing the track. But we still don't have a solution for our problems. Slow motion cameras help to decipher what's going wrong. If the wheel slips just slightly and starts to go out of sync, the grippy surface we thought would help, in fact, then makes things worse. It's almost like as the speed goes up, it would want to be slippier, to give it more time to drop back
Slippier or grippier?
Slippier. So I gamble on sanding off the grippy paint in the grooves on the track and covering the rubber on the corners of the wheels. In order to make it slightly self-correcting, we're trying to get the corners to have very little friction. So as it goes out, they can just slip back in, just fractionally, and then the whole thing stays on the straight and level, as they say. It's a fine compromise between high-level mathematics and real life. After yet more rain, the tests are not exactly confidence-inspiring. I've still not been able to drive anywhere near fast enough to make a jump. And as if I wasn't under enough pressure already, Liz and Dallas then turn up.
Is this seriously it? Gemothy, what the heck?
It's, I know it looks...
It looks ridiculous.
Yes, insane. We don't know if it's definitely going to happen, if it's definitely going to work, but as far as we're aware, nobody in the world has ever jumped anything on a square-wheeled motorbike.
So on a scale of 1 to 10, what's your confidence levels?
This is mad.
It is mad.
I think that either I'm going to end up catching something, ploughing into this plywood and just face planting onto there. Or I'm going to go soaring over the top like an eagle.
So 1 to 10, we're talking 50-50 then? 5?
I would say it's not that good, 30-70.
You're fine. It's fine.
Thank you, Dallas.
James, you know what? Let's just get it over and done with because I'm beginning to like hyperventilate.
Yeah, thank you, Liz. Thank you. Liz is right. I've now just got to do it. This is the moment of truth. My reputation, my health, my pride, all rest on whether I can jump a square-wheeled motorbike off a 45-degree ramp.
That was fantastic.
You are such a hero. That was amazing.
That was great. It was really smooth. Right up until the end, it was really smooth.
You made it look so easy.
You got about 10 inches.
I know. Biggest jump ever on a square-wheel bike.
It looks so wicked.
Maybe not the distance that Knievel aimed for.
Yeah, but it was style.
Style.
Yeah, you got the style
You got
point.
the style down, hon. You really did.
Guys.
Well done, babe. Well done.
It was good, but I just know it can be better. So I go back and try it again.
Ben's like ice cool. He's like Iceman.
I know. He's so calm.
The Iceman cometh.
If he gets
Wait, he's
up.
gone. He's bottled it. He's gone.
Is he gone for a whiz? He's gone for a final nervous
He's just
whiz
gone for
behind the
pee
trees.
behind the-
Brilliant.